So it's my pleasure to introduce to everybody Yang Yu, who's a PhD candidate at Berkeley. His advisor is Jim Dennell, and he has been doing a lot of really interesting work on essentially crossing HPC parallel algorithms and machine learning, deep learning. And he's had a lot of adoption of his work in industry. And I will turn it over to him to tell you more about it. But before I do, I want to kind of fill people in on the sort of the Zoom protocol here. So everybody is joining muted. So if you'd like to ask a question, type something in the chat window that alerts me, and then I can sort of mediate those questions and then interrupt Yang at the appropriate moments, and then you can unmute yourself and ask the question and then mute yourself again. Okay. So without further ado, go ahead, Yang.
Okay. Thanks, Michael. Thanks for the introduction. Firstly, so can you hear me? Can you hear me good? Hi, Michael.
Yes. Yeah, it's fine.
Okay, good. Yeah. So today my talk is about how to train deep learning model very fast. So let's go to my talk. So here is an outline of my talk. So in the first part, let me briefly introduce. So why is deep learning slow? So we know actually in the last 3 years, supercomputers, I mean the HPC high performance computing techniques are becoming more popular to the leading AI companies. For example, Microsoft put some supercomputer to the cloud. So now Google has its own supercomputer TPU pod, tensor processing unit pod. Pod like means a bunch of TPUs connected by high-speed network. And Facebook made some mention to the top 500 supercomputer list. So Amazon has HPC Cloud, which is for the supercomputing application. So here are two quotes from deep learning researchers. From the two quotes, you can see that actually supercomputers are becoming more popular. So why they like supercomputers? Is something okay? Good. So why they like supercomputers? Because the computation of deep learning is very expensive. For example, if we want to use ImageNet to train ResNet-50 model, we need to finish 90 epochs. So each epoch we need to process 1.3 million images. And for each image, we need to finish 7.7 billion operations. So in total, it's 10 to the power of 18 operations. So if we only use one CPU, it's going to take us several months. It's like forever. If we use one M40 GPUs, it's going to take us 14 days. So even we have 8 powerful P100 GPUs, it will take us 29 hours. So this, the training is very time consuming. However, we know in 2017, actually the best supercomputer can finish 2 times 10 to the power of 17 operation per second. So the first question is, can we just use supercomputer to finish the ResNet-50 training in 5 seconds? The answer is no, because we cannot make full use of supercomputer. And why and how can we make a full use of supercomputer? Let me explain later. But before that, let me briefly go over the foundation of deep learning. And also it's very important to my talk today. So mini batch SGD, stochastic gradient descent. So I want to make this algorithm as simple as possible. At each iteration, we take a bunch of data from the memory, and we compute the gradients of the loss function by the data. And then we use the gradients to update the weights. So there are some notations here, like by each side, learning rate, weights, the sample, loss function, and the gradients. So here I just want to make this algorithm as simple as possible. It only has 3 steps each iteration. So let's go to the first question. So why we cannot make full use of supercomputer, and how can we make full use of supercomputer? So we know now the single processor frequency stop scalings, which means we don't have free lunch now. By free lunch, I mean in 20 years ago, we can just wait for 18 months on our code 2 times faster. But now, if we want to use supercomputer to speed up deep learning, modern supercomputers often have thousands of processors. So the idea here is how can we parallelize deep learning over thousands of processors? Okay. So actually, there are 3 different approaches to parallelize deep learning over thousands of processors. We can parallelize the data, and we can also parallelize within each layer and across different layers. But for now, model parallelism is very limited. So in this talk, I'm going to talk about how to do the data parallelism. So let's go to the first direction, how to parallelize the data. So here, I just want to give you a toy example to show the key idea here. So how to do data parallelism. And here we have 6 data samples. We partition them to each node. Suppose we only have 3 nodes. And each node will do a local forward pass and backward pass on its own data. And then each node will get its local gradient. And then we do an all-reduce operation for all the gradients and to get the average of all the gradients. And this average is a global gradient. We send this average to all the nodes, and each node will use the global gradient to update its local weight. So here clearly you can see how to increase the parallelism. We just need to increase the batch size here. So large batch training probably is a solution for this project. How can we make a full use of supercomputer for deep learning? So here by large batch training, I mean we fix number of epochs and increase the batch size. So here, let me give you a table. The first column is batch size, and the number of epochs, and the number of iterations, nodes, and the single iteration time. So here, I mean we fix number of epochs. We increase the base size here, and because number of epochs is fixed, we are reducing the number of iterations. So actually here, T1 is the computation time, so T2 is the P2P communication time. So I mean recently, people show T1 can be much larger than T2 for the ImageNet training. So here, let's just assume so T1 is much larger than T2. So actually, you can see as if we increase the base size and also increase the number of nodes, so the single iteration time can be roughly constant, right? Because T1 is much larger than T2, and also we increase like the number of nodes by p times. The T2 part they only increase by log p times. So single iteration time can be roughly constant, and we are reducing the number of iterations. So which means the large batch training potentially can give you a big speed up if we do that and increase base size and increase the number of nodes. Okay.
And Yang, just a clarification on that slide. So batch size is is essentially the number of data points that you run through the current version of the neural network before you aggregate the error, and then you use that to update the neural network. Is that right?
Yeah. Per iteration, every iteration. Yeah.
So by having a larger batch sizes, you're hoping that you're accomplishing quote kind of more learning per unit time, and thus we'll be able to use fewer iterations and converge more quickly. Okay.
Yeah. Per iteration, and then we wanted to like to learn more from the data. I mean to have a large. More data samples in each iteration. Yeah.
Okay, great.
Okay, thank you. Thanks for asking. Yeah. So large batch training is good, and it potentially can give us a big speed up. So however, actually large batch training is not easy. So here, let me give you a figure. the horizontal axis is number of epochs. The vertical axis is accuracy. Let me give you two lines. So the first line is the baseline, and the second line large Bayes training. So clearly, by training the same number of epochs, very easily large Bayes training will lose accuracy. Clear the gap between the large Bayes training and the baseline. So here the challenge is we need a good implementation, we need a good hardware, but I think we also need a good numerical optimization algorithm, because large Bayes training is a hard numerical optimization problem. Why? So because I mean the accuracy actually very important to deep learning. For example, if we want to use ImageNet to train ResNet model, we need to achieve 76%, roughly 76% accuracy in 90 epochs. So actually 76% accuracy is very different from 75% accuracy, because 75% accuracy only needs 60 epochs. So here is a quote from Andrew, and from this quote you can see. So the last 1% accuracy is actually very important, but it's very hard to achieve. So the accuracy is very important to deep learning, but we know large Bayes training is going to lose accuracy. So that means even we can have a huge speed up, our results are terrible and our accuracy low. It's not meaningful. So we need to not only make the deep learning run faster, we also need to make them get the same accuracy. I think that's the top priority of this talk. How can we make it make the training run as fast as possible and also get the peak accuracy? Yeah. So the next part, let me introduce. So why is scaling deep learning difficult? Why it's not easy? Okay. So for here, let me introduce two papers. So the first paper by Intel, second paper by Facebook. So I want to explain so why we lose accuracy. Let me introduce the two papers one by one. So the first paper by Facebook, idea is it's a generalization problem. So here, let me give you a figure. The figure from Intel paper. So there are two lines. So the first line, the black solid line is the training function, and the dashed line, the color is red. The red dashed line is the testing function. So here, flat minimum means baseline, and sharp minimum means the large Bayes training. So because it's loss function, lower is better. Lower is better here. So now let's draw a vertical line at the minimum of the solid line, or a minimum of the training function. Let's make a vertical line here. So let's see where is the intersection between this vertical line and the testing function. So now we can see something interesting. So for the flat minimum, for the baseline for small Bayes training, so if our training loss is low, our testing loss is also low. But for large Bayes training, so even our training loss is low, but our testing loss is very high. So which means even we can train a good model, it's very hard to generalize for large Bayes training. We can get a high training accuracy, but our testing accuracy is low. So that's bad. That's the first paper by Intel. So let me also introduce the second paper by Facebook.
So Yang, before you continue, I think we have two questions. One is from Christian. Maybe Christian, you can unmute yourself and ask the question.
Yeah, so my question is, wouldn't this same problem be there for small batch training also? Because there is a shift between training minima and the testing minima.
I'm sorry, can you say again? I'm so sorry about that. It's not very clear.
So my question was, wouldn't the same minima shift problem be present for both small batch training and large batch training? Why is it only for large batch training?
Okay. So thanks for asking. So let me go back to here. So sorry. So here we have the baseline small Bayes training and large Bayes training. So they are trying to solve the same problem, but they get different accuracy. which means they give you different solutions. So live training gave you a better solution. Is that clear? Can you hear me?
Yeah, I can hear you. So my question was like, why the accuracy is different? Because
Okay, good. So your question is why accuracy is different, right?
yes.
Okay, so because I mean, they can by training them, you get different models, but because they converge to a different local minimum. So the small batch, I mean, converge to a good local minimum. Live batch give converge to bad local minimum. So even the training accuracy, they are the same, but because the live batch training converge to a bad local minimum, it's hard to generalize. So testing accuracy is low. So is that clear?
Yes, that's clear.
Okay, thank you so much. Okay. Hi, Michael. Can I continue?
Yeah, go ahead, continue, please.
Okay. Thank you. Yeah, so let me also introduce the second paper by Facebook. So here the horizontal axis is a number, is the batch size. The vertical axis is the error rate. Lower is better. So clearly Facebook gave us very exciting results. So they can scale the batch size from 64 to 8K. You see, they get the same accuracy. This line is very flat from 64 to 8K, which means they get the same accuracy. So when we increase the batch size to 8K. So by doing so, now Facebook can use 256 GPUs and make the training very fast. So let me briefly go over the techniques by Facebook. So key idea here is how can we auto-tune the hyperparameter like learning rate? So the setting is we want to fix number of epochs, because we know fixed number of epochs, fixing the number of epochs means fixing number of floating point operations. So the first idea is linear scaling. So when we increase the batch size from B to KB, we should increase the learning rate by K times. So why should we do that? Because we increase the batch size by K times, basically we are reducing the number of iterations by K times. We know the number of iterations equal to the number of updating. So basically, we are reducing the number of updatings by K times. So to make each updating more powerful, we just increase the learning rate by K times. Yeah, that's a key idea. And the second idea is a warm up. So after we use the linear scaling, we are going to have a huge learning rate if we use a huge batch size. However, we know in the beginning of the training, the gradients are changing very fast in the beginning. So if we use a huge learning rate in the beginning, very easily our network can diverge. So the idea here is we want to start from a tiny learning rate and increase the learning rate in the first few epochs. That's the second idea. So Facebook use linear scaling and warm up, so they can scale the batch size to 8K. So, and they use the ResNet 50 as an ImageNet training with ResNet 50 as an example. So now we want to move the approach to different model like AlexNet, and we found something different. So here we use this approach to AlexNet, and we found that when we increase the batch size from 512 to 4K to 8K, we will lose accuracy. You see, we can only scale the batch size to 1K. So even we use a warm-up linear scaling, we tune learning rate, momentum, with decay, and we do data shuffle, data scaling, and also do the learning rate decay. So they didn't work. And let me give you more data. According to Facebook, we increase the batch size 8 times. We also should be able to increase the learning rate by 8 times. But sometimes, but in some situation, even we increase the learning rate by 7 times, the network can diverge. So the first conclusion is the Facebook approach doesn't work for other models like AlexNet. So even we use linear scaling warm up and we tune almost all the hyperparameters, they didn't work. Yeah, that's the first concern by Facebook approach. And second concern, let's go back to Facebook the figure from a physical paper. So you see, so they increase the base size from 64 to 8K, right? They can get same accuracy. But when we increase the base size to 16K, we lose accuracy. To 32K, we lose accuracy. To 64K, we lose accuracy. So the second concern is the physical approach only works for base size, below 8K. So if we want a very light base size, physical approach doesn't work. So that's the second concern. So we want to have a new approach that can work for very light base size. And there are number three concern. We know deep learning has many other applications like BERT, right? So BERT is a state-of-art NLP model. So actually, the baseline of BERT used Adam W as the optimizer. Here, W means weight decay. So here is Adam optimizer with weight decay. So the baseline used a base size of 512 and can get F1 score of over 90 for the squad application. However, and when we increase the base size to 16K, and no matter how we tune the hyperparameters, we cannot reach F1 score of 90. So the best, even we significantly tune the hyperparameter, we can only get F1 score of around 88. We know the last 1% are actually very important. So number three challenge is, so can we make light-based training work for other applications like BERT? So can we scale the base size of BERT to very large? So that's number three challenge. So in the next part, let me introduce our approach to solve this problem to scale the base size to very large without losing accuracy. And I'm going to explain why they work after I introduce the approach. Okay, so we did some numerical experiments and found something interesting. So here, let me just use AlexNet as an example because AlexNet only has 8 layers. It's easy to visualize. So let me give you a table. The first row is the layer ID. We have 8 layers. And for each layer, we compute the norm of the weights for each layer. And we compute the norm of the gradients for each layer. And then we compute the ratio between them. Now, we found something very interesting. For example, for layer 6, this ratio is over 1,000. But for layer 1, this ratio is only around 6. We know in 2017, almost all the applications, deep learning applications, they use the same learning rate for all the layers. So that's okay for the smart batch training, but for light batch training can be a problem. Because after we use linear scaling, so layer 6 may have a huge learning rate. But if we use this same learning rate to layer 1 may diverge. So let me give you a better figure to visualize that. So here, the horizontal axis is layer ID. The vertical axis is the ratio I mentioned before. So you see this ratio. So layer 6 is very high, but layer 1 is ratio is very low. So here a top example. So maybe layer 6 is okay, but if you use the same learning rate for layer 1 will diverge. So that's a concern for light-based training. So based on this important information, so we propose the idea of a trust ratio. So here, let me define the trust ratio. There are some notations here. So layer ID and batch size, iteration ID, and also we compute the gradients for each data points and then do the average. And then we get the average of all the gradients. And then we use weight decay. So after that, we can have something like that. We name it as a trust ratio. So you see trust ratio for a given layer at each iteration. So trust ratio, the first part of trust ratio is the norm of the weights for each layer, and also the norm of gradients for each layer, and also with the decay. So under standard global Lipschitz condition, so we can treat the trust ratio as the estimate of the inverse of the Lipschitz constant. I'm going to explain later why this works. I'm going to explain. So, but before I explain why this works, let me introduce our algorithm. So we want to use the trust ratio to build a new algorithm. So the first algorithm is large. So here, actually, I want to make it simple because I only include the key updating part. So the algorithm also has some initialization, I mean, some trivial parts. So here, let me just focus on the updating parts. So there are notations, there are some notations here. Let me explain them. So batch size, learning rate, weight decay, scaling function, and the data sample, loss function, gradients, and the coefficient of the momentum. So let me slowly go over this approach. So within each layer and at each iteration, first we compute the gradients, and then we initialize the trust ratio. So we compute the first part of the trust ratio by the norm of the gradients, and then we compute the second part of the trust ratio by layer-wise with the decay. And then after the trust ratio is okay, so we use the trust ratio to update the momentum, and then we use the momentum to update the weights. So the key idea here is each layer will have its unique learning rate. And also because we know the trust ratio is changing between different iterations, so it can give you kind of adaptive scaling at the runtime. Actually, I mean, that's the first algorithm loss. We can make it even better. So let me introduce the second algorithm, and then I explain why they work. So the second algorithm is LAM, layer-wise adaptive moment for batch training. So we know in the last few years, I mean, optimization of deep learning, I mean, changing very fast. So here, let me just put some new techniques together with the trust ratio techniques. So again, within each layer and at each iteration, first within each layer we compute the gradients. We compute the first moment and the second moment, and then we do the bias correction for first moment and second moment, and then we initialize the trust ratio. So then we compute the first part of a trust ratio. We compute the second part of trust ratio by element-wise with the decay. So after the trust ratio okay, we use the trust ratio to update the weights. I mean, there are some notations here I introduced in the previous slides. So let me just briefly introduce the key idea here. So the key idea is you can have adaptive element-wise updating and layer-wise correction. Because this is within each layer, it's layer-wise correction. And speaking of element-wise updating, because we know we use a technique, for example, by Adam. So here you just use element-wise, kind of, you can get more information. And also we use element-wise with the decay here. That's very important for the huge model like a bird. They have billions of parameters. So that's the second algorithm, LAM. So I introduced large and LAM. So now the one more important thing is I want to explain so why large and LAM work. I want to answer 3 questions. So why large and LAM can solve a sharp minimum problem, and why they can speed up training, and why they can converge faster than IGG. So let me talk about that. Talk about them one by one. So first, let me introduce the dynamics of large. So you see those. So the horizontal axis is number of epochs. The vertical axis is the learning rate. So here I use AlexNet as an example. Here, layer 1, the convolutional part. Sorry, here is the bias part. And here, layer 5, also convolutional layer. Here, weight part, here, bias part. And we have a base size 256, base size 1K, base size 8K. So the first thing we can see here is for different layer 1 and layer 5, you see learning rate is very different from each other, right? So you see the vertical axis, the range is very different, and also the curve is very different from each other for different layer first. So even within the same layer, so layer 1, the weight part, the bias part, they are also very different. And for a different iteration, I mean, because the apples kind of proportional to the iteration. For different iteration, you see the learning rate is very different. And also a different base size will use different learning rate. So this is a dynamics. This is dynamic of loss. They are actually very important to the optimization. So why? We know we want to use loss and lab to solve the sharp minima problem. So the first question is, so why small batch can solve this sharp minima problem? Because small batch actually use the noisy gradients in the step computation. So actually this noise is very important. The noise can push the optimize out of the attraction of the sharp minimizer. And we know when we increase the batch size to very large, and we are reducing the noise, and this noise in library is not enough to help the optimizer get out of the sharp minimizer. So that's why a small batch can avoid the sharp minimizer. So the idea here is, so can we add some noise to library training to make it convert to a better local minimum? Yes, I think we should be able to add some noise, but how? Actually, we tried adding the common Gaussian noise, and also significantly tuning hyperparameters. But it didn't work. For example, we add noise to the activation, to the weight, to the gradients, to the output. So we actually significantly tune the hyperparameters. They didn't work. So actually Intel team also did the same thing, and also it didn't work. If you want more, please check their paper. So here I want to say maybe the dynamics of loss and lab can be a proper noise. So if I go back to this slide, you see, so I mean, it's kind of dynamics, a kind of proper noise between different iteration and also between different batch size. So I believe they can be a proper noise. So maybe this proper noise can help the optimizer get out of the sharp minimizer. So that's the first part of the explanation. And the second thing I want to implement, so why they can speed up training. So here, let me give you another figure. Actually, this figure is a 3-dimension figure. So here is the first dimension is the trust ratio, and the second dimension is iteration, and number 3 dimension is the frequency. So higher means you have a high frequency of the trust ratio. So you can see. So I mean, in the training, you see, if we use a loss as an optimizer, so in the beginning, so almost all the trust ratio are tiny, right? So we know we use the trust ratio to update a lane rate. So after the trust ratio is tiny, so the learning is very slow. So actually, because in the beginning all the trust ratio are tiny, so it can be a natural per layer warm-up. And also we can see across the training process, some of the trust ratio are always small. So actually, that's also very important, because this can encourage the stable layers to use aggressive lane rate without a divergence or without diverging. So without trust ratio, I mean, some weak layers may limit the overall lane rate, and because you use a huge lane rate, I mean, some layers good, other layers are not stable. So the weak layers will diverge. So the overall system will diverge. So I mean, that's why trust ratio is important. It can it can help the stable layers to use aggressive lane rate without diverging, and also give you a per layer warm-up. Yeah, that's the second part. And the next part is convergence rate. So actually, in the general non-convex setting, we can prove loss and lab can converge to a stationary point in the general non-convex setting. So I think that's the best thing people can do now, because we know the non-convex optimization is a NP-hard problem. So we cannot prove they converge to a global minima. We can only prove they converge to a stationary point in a non-convex setting. So on the second part, we can prove that loss and lab can converge faster than IGD in the live-based training. Because the convergence rate of IGD we know depends on the maximus of the smoothness across dimension or the maximum of the Lipschitz constants. But the conversion rate of our large lab only depends on the average of the Lipschitz constants. So which means the conversion rate of large lab much faster than IgG. So if you want to know, I have more details in my backup slide. We can talk in the QA session. So let me briefly sum up. So why large lamb work? Because it has a high conversion rate, and also it can be a proper noise to help optimizer get out of the sharp minimizer. And also it's a natural polymer warm-up, and it can avoid network divergence even we use a huge lane rate. So that's the reason why they work. Okay, so next part, let me briefly introduce the experimental results and also the applications of our algorithm. So as I mentioned before, feasible approach doesn't work for AlexNet. We can only scale to AlexNet base size to 1K. But here, if we use LARS, we can scale the base size to 4K to 8K, and we can get the same accuracy and in the same number of epochs. So even we add a base normalization, we can get the same accuracy. Okay. Yeah, so feasible approach for ResNet only scale base size to 8K. We can scale to 32K or 64K. So here is an example of 32K. So you see the horizontal axis in number of epochs, vertical axis is testing accuracy, higher is better. Clearly, you can see there are two lines. The first line is our approach large, and the second line is the baseline. You see, by training the same number of epochs, now we can get the same accuracy. And also, we want to have a comparison between our approach and the state of the art approach. So the horizontal axis is the base size, vertical axis is the error rate. Lower is better. So you see, no matter how we change the base size, our approach is better than the state of art approach. And also, when we increase the base size over large, our approach is much better. You see, so here lower is better. Yeah. So I also want to mention, I mean, the BERT, which kind of a very important application today. So as I mentioned before, we scale the base size of BERT to 16K, we will lose accuracy. But now, and with our approach, you can scale the base size to 32K or even 64K. So here, the first column is the optimizer, second column base size, and a number of steps, and also F1 score higher is better, and the number of TPUs and the wall clock time or training time. So you see, we can actually reduce the BERT training time from 3 days to 76 minutes without losing accuracy. We can get the same F1 score. Yeah, so let me give you a better picture to visualize that. So the horizontal
here, we had a question from Wen Tao.
Okay.
Go ahead.
Please.
So I'm wondering what's the difference between LARS and other adaptive optimizers such as does LARS like entirely replace ADAM, or do they work together to adjust the rendering?
Oh, okay. Very good question. Thanks for asking. Maybe let me go back to LARS and LAMB. So here LAMB, here LARS. Yeah, probably so LARS is built on top of momentum. So actually, you can see. So here is the trust ratio, right? So here trust ratio, right? So after the trust ratio is only one, so it's essentially the same with the momentum IgG, right? Hello, can you hear me?
I mean,
okay.
Yeah. What's the? I'm just wondering, is it the rendering rate adjustment on top of ADAM? Do you know ADAM like?
Yeah.
Or is it on top of purely SGD?
So actually, LARS is on momentum IgG, LAMB is on ADAM. So here LAMB, you see, I think the difference here, right? We have the trust ratio. So if you just manually set the trust ratio as 1, you kind of go back to ADAM.
I see. Thanks.
Okay. Thank you. Thanks for asking. Okay. Yeah, so now I think we can scale to 1K TPUs without losing accuracy. And here, one is perfect scaling, second one is our scaling. You see, sometimes we can even beat perfect scaling, and I think our speed is very good. Yeah, so actually there's another challenge here. So the challenge is, so how can we auto-tune the hyperparameter every time we change the byte size? We know a bigger company like Google, they have different teams. So a different team will need a different byte size, right? For example, Google Translate may need a byte size of 48K, YouTube may need a byte size of 16K, so Gmail may need a byte size of 32K. So it's really annoying and time consuming way to all the hyperparameters every time we change the byte size. So even for an expert or auto tuner, it's not easy. So I think the second challenge is how can we auto tune the hyperparameters every time we change the byte size. So actually, if you use our LAMP optimizer, you don't need to tune any hyperparameters. So here, let me give you a table. So the first row is the byte size, second row is the lane rate, and the warm up and F1 score. So you see, if we increase the byte size by k times, we just need to increase the lane rate by square root of k times and increase the warm up by k times. We can get the, no matter how we change the byte size, we can get the same accuracy. You see, here we increase the byte size 2 times, 2 times, 2 times. We just increase the lane rate square root times, square root 2 times, square root 2 times, and increase warm up 2 times, 2 times. We can get the same accuracy. So we don't need to any hyperparameters if we use LAMP. And also another challenge is we know there we don't have a general optimizer yet to the best of my knowledge. So the traditional optimizer like Momentum IGD, they work very well for ImageNet, but they failed on the NLP like BERT, NLP application like BERT. On the other hand, so Adam, the adaptive optimizer Adam, they work very well for NLP like BERT, but they failed on ImageNet. So I already showed you, so LAMP worked very well for NLP, but will LAMP work for ImageNet? So actually, we did some numerical experiments. We found LAMP worked very well for ImageNet. So here, the horizontal axis is a different optimizer, vertical axis is accuracy. You see, so in some so if we increase byte size to 16K, so LAMP can even achieve higher accuracy than Momentum IGD. So to the best of our knowledge, so LAMP is the first optimizer, so working for both BERT and ImageNet training. I mean, so here, I mean, working means you get the top, the same accuracy, I mean, the best accuracy. So in the next part, let me briefly introduce the application approach in the, our approach used in the real world applications. So we know in the last 3 years, so people reduce the ImageNet training time from like 29 hours to 1 minute. So here is a table is ImageNet training speed world records. So actually, I'm very happy to say, so since 2017, all of them use my large algorithm. So for example, the ImageNet training speed world records were created by Facebook, Berkeley, Japan P11 company, Berkeley, Tencent, Sony, Google, Fujitsu, Google again. So you see, so since 2017, so all of them use my large optimizer. So I'm very happy to say so Lars made a contribution in this area. Okay. Yeah, and I just want to briefly mention, so we won the best paper award of ICPP. So it's actually the most cited HPC conference paper in the last 3 years. So it's being used by many leading AI companies like Google, Facebook, or Intel. And I want to mention, so even for some deep learning researchers, they can implement our approach in their own application. So here is a quote from a deep learning researcher at Stanford. So clearly you can see even for the small batch training for the regular application, you can just implement the large, can make your training run much faster. And recently, so even Jeff Hinton team say they use RARS to achieve the state-of-art ImageNet classification results. I mean, the paper published recently, if you want more, please check this paper. So I'm very happy so Lars can also use it in the regular applications. And Lars was added to MLPerf, which is the industry benchmark for fast deep learning. So yeah, we know MLPerf includes Google, Intel, and NVIDIA, many different companies. And also we got some media coverages under Lars, for example, communication of ACM and National Science Foundation. So NextWeb. Yeah. So let me also briefly introduce early success of LAM. So actually, so here, this figure is from the blog post of FastAI, which is a Silicon Valley startup for fast deep learning. So LAM will help FastAI to scale the transformer model to 128 GPUs. So here is a quote from FastAI. So clearly from this quote, you can see, so even on single machine, so LAM is much better than Adam. If you want to know, please check FastAI blog post. And also, so LAM actually becomes an official advisor of NVIDIA. So here is a screenshot from NVIDIA public GitHub. So according to NVIDIA public GitHub, here is a quote, right? So LAM is 17 times faster than Adam. So here actually a good implementation. If you want to use LAM, please check NVIDIA public GitHub. So according to NVIDIA, so LAM is 17 times faster than Adam optimizer. Okay. And so LAM helped Google to achieve state-of-the-art results on GLUE, RIS, and SQuAD benchmarks. So they are the World Cup for NLP. And also it's being used by the state-of-the-art NLP model like Albert. If you want more, please check those model and the paper. And also, so even some small companies, so they are using LAM. So here's a quote from a research scientist in a small company. Yeah. So one last thing I want to mention. So actually, our research was mentioned in Google production release. So actually, Google now are now using Lars and LAM to make the deep learning run very fast. Yeah. So the next part, I have 3 minutes. So let me briefly introduce my future work. Okay. So I think that the first direction is a short-term research plan. So it's a natural extension of my current research. Because we know, so why deep learning is better than traditional approach. So because we give deep learning a larger data set and make the model larger, they give us better results. But now I think we are still here. We still have lots of potentials for deep learning. So in the future, I will give deep learning more data and even larger models. We can, I believe, we can even get better results. So I think probably in the next 5 years, supercomputers are still very important to deep learning. And for example, actually, I think AI supercomputer is very promising now. I mean, for example, there are some exciting projects even from academia. For example, Hammer Blade from Michael team, and also recently, so NVIDIA actually put the DGX the super pod to the production line. It's kind of has 1K. I mean, in the future, NVIDIA probably will sell you a supercomputer with 1K GPUs. So like something like super pod. And also the Google next generation TPU pod is 4 times larger than today. So I think there's too many things to do in this area. So we need to build a more scalable and more robust optimizer for the AI supercomputer in the next 5 years or 10 years. And the second direction is federated machine learning. So we know actually there's a concern in the current deep learning system. So we need to collect the data from the user. So a user can be a person. For example, your photo in your cell phone is your data. A user can also be a hospital. The medical records are the data. So probably because the data is very important, some users probably don't want to share the data in the future. So we need a new approach for some applications. I think federated learning may be a promising direction. So which means because federated learning can help the user to then learn their own model without sharing the data. But there are several different features of federated learning can be a challenge. First is a massive parallel. For example, in the future, Google's app can help billions of users. I think that's possible. And also the data is highly non-ID. So I don't know your data, you don't know my data. So it can be a challenge for traditional optimization. And also the data is unbalanced. Some nodes have many samples, other nodes have maybe has many thousands of samples. I mean, other nodes have tens of samples. So the load is very unbalanced. And also the communication is very limited because only a few rounds of unreliable communication are possible. So here I just want to mention, so there are some exciting UDA project like a Parameter Hub and P-Links. Probably I can collaborate with those folks to make federated learning work for this part. And also the async, and we have to do the async communication because we cannot force the user to updating at 7 a.m. or 10 p.m. And also my number 3 direction is energy efficient machine learning. So we know, actually last year I took a flight from San Francisco to New York. Sorry. Let me finish my talk in 1 minute. I'm finishing very quickly. So last year I took a flight from San Francisco to New York. We know it's going to cost some energy, right? But this energy cost is much lower than training a deep learning model. Actually, that's ridiculous. So we need to reduce the energy cost in deep learning. Otherwise, it's very hard for us to deploy deep learning in the real world application. So for example, there are promising how can we reduce the tuning errors? How can we minimize the cost of data movement and floating point operations? And hopefully I can do something and make contribution to TVM. Let me briefly introduce in the last 3 years. So I did some research to make machine learning run faster on supercomputers. So even for the traditional machine learning like SVM, we can make them 16. We can make SVM 16 times faster. So we win the best paper award of IPDPS, and we can train ImageNet in 15 minutes on CPUs. So here is CPU. We don't use GPU or TPUs. We can finish it in 15 minutes. So we won the best paper award ICPP. So we publish our research on the supercomputing conference like SC, ICS, or IPDPS. But we can also publish our research on the leading AI conference like NeurIPS and ICRR. I want to mention recently we reduced the bird training time from 3 days to 76 minutes. Thanks so much. I'm very happy to take questions.
That's great. Thank you.
Thank you
so much, Yang. Do we have any questions from the audience?
Well,
oh, go ahead, Louise.
Yeah, I'm just curious. So you, this is a really awesome, super interesting results. I'm curious if you have thoughts on how to apply these techniques to less controlled environments, like instead of supercomputer scenarios where you actually have full control of the machine, you have more of a cloud-based environment where you have to take into account dynamic loads and changing interconnection network behavior and so on.
Thanks for asking. I think a very good question. So I just want to confirm. So you mean, so if I move my project, for example, to the cloud, maybe we should worry about the performance. Maybe my approach is not accurate, not fast enough. Is that your question?
Oh no, I'm not sure. I'm just curious. I didn't mean to imply it was not fast enough. I'm just curious whether you think it applies to more dynamic scenarios where you can't rely on as a well-behaved and well-controlled environment of the interconnection network.
Okay. Thank you so much. Thanks for asking. Yeah. So I think because we are working on a numerical optimization problem, so I think probably it will work on cloud, even we have less control. For example, we have 100 nodes. I mean, maybe it's a very very likely in the training, like maybe 50 or 60 nodes can done, will be done in the middle of training. And I think my project can still give you a roughly the same accuracy. Is that clear? Did I answer your question?
Yeah, that's clear. Yeah.
Okay,
Thank you.
okay. Thank you so much.
Oh, that's very interesting. I hadn't thought about that. When you aggregate all the data, you could just drop out nodes that happen to have died. That's pretty interesting. So I had a question about, in terms of numerical optimization, you know, it looks like your improvement operated like at the layer level.
Yeah, yeah.
Wondering, you know, is there the possibility that layers end up being kind of heterogeneous in what they do, like so that you might actually need to optimize different portions of a layer differently based on how they're evolving as they get trained?
I think actually that's a very good question. So I actually do you think I'm doing the same thing? I mean, in the direction, but because for us, different layers they are different, so they will learn at a different speed in our approach. I mean, can you say more?
Well, I just mean like,
okay.
I think currently, like you are tuning the parameters on a layer by layer basis, right? Like automatically.
Yeah.
And I'm just wondering if it may be that there's heterogeneity within a layer. And thus you might actually want to tune the parameters, like even within a layer, you might.
Oh, okay. Oh, I see. Okay, you mean even within each layer, right?
Yeah.
Yeah. So, but because our approach is, for example, LAM approach is built on top of Adam optimizer. So Adam actually already take this into account. So for I feel like let me go back to the slide. Let me explain. Okay. Yeah. So you see. So here first within each layer. So actually Adam is doing something element wise. So here this operation element wise. So
okay, I see.
Yeah. Okay. Yeah. Thank you.
Christian had a question.
Okay.
Why don't you go ahead, Christian?
Hey, I had a question. I wanted to ask whether we need to change any other hyperparameter except for the learning rate and the warm-up proportion.
You mean any other parameters should we care about?
Yeah.
Okay. Yeah. So I think with the decay actually also very important, and I mean for this project we found you only need to care first learning rate and the warm up, because warm up and learning rate they are kind of very related to each other. You can treat them as one parameter, one hyperparameters. So another important is with the decay actually because we know we want to solve this sharp minima problem. It's something like the overfitting. So I think with decay is also very important. Did I answer your question? Do you want to know more?
Yeah, I mean, how do I know how to tune weight decay?
Okay, good question. Very good question. So for now, I don't have a good answer. Usually, we start from application. The application already give us a default with the decay hyperparameters. So we just use the default. For now, we didn't tune with the decay. How about let me do some study and maybe come back to you later. Is that okay?
Yeah, that's okay.
Okay.
I had one more question.
Okay.
You said we need to double the warm up if we are doubling the batch size, right? So what is the reason behind this? Is the reason that the model needs to stabilize more?
So your question is why double the base size and then I double the warm up or learning rate? Is that your question?
Yeah.
So because I mean, we increase base size, we are reducing the number of iterations, right? so our updating, I mean, is much fewer than before. So we want to make each updating more powerful, which means we want to make each iteration learn more. So we want each iteration learn faster. So we want to double the we want to increase the batch size. So but if you increase the batch size very easily, it can diverge. So you also want to give them a longer warm-up period. So we want to make it stable. I mean the quick answer is we want them to learn fast. Also, we want to make them stable.
Yeah, okay, that answers my question. Thank you.
Oh, thanks for asking. Thank you.
Okay, great. Any other questions before we wrap it up and thank Yang? Okay, great. Well, thank you so much for attending, and thank you, Yang, for presenting.
Okay, thank you. Thank you so much.